Hello and welcome to lesson 3.6 optimization problems. In these kinds of problems, what we're going to do is we're going to use our skills with algebra and set up two equations, one of which we're going to find an optimal value. We can either use this first derivative test or second derivative test to test these to verify if you get an optimal value, in other words, a maximum or minimum. So let's get started. So a rectangular lot is enclosed by fence and is subdivided into three equal-sized lots, as you guys can see in the diagram, using fence. Determine the dimensions of one lot that would maximize area if the fence must be a total of 2,400. So let's create two equations. First of all, I don't know what the area is, so I'm going to call it A. And I know the area is given by length times width. Now you could also multiply this by 3, because if you're maximizing the area of 1, you're maximizing the area of all 3, but not necessary. So I'm going to call this equation 1. Also notice that I have various areas, various widths that are here, and I have 4 lengths. So I know I have 4 lengths plus 6 widths is equal to 2,400 meters. So from here, what I can do is I can solve for either L or W in the second equation. I'm going to solve for L in the second equation. And I should also define the variable A. So let A represent the area of one lot. L and W are already defined for us in the graph or the drawing, so it's not necessary to redefine. Okay, so in one of these equations, you'll notice that you can solve for any one of the variables. So I'm going to do that. So this gives me 2,400 minus 6W. So L is, divide everything by that, so it gets 600 minus 3 over 2W. Okay, so from there, what I can do is I can substitute that in 1. So that'll give me an area that is 600 minus 3 over 2W times W, which I'm going to simplify to 600W minus 3 over 2W squared. So this is the function I want to maximize. I want to find the maximum area here. So to maximize the area, I need the derivative. Okay, so that turns out to be 600 minus 3 over 2. Oh, my apologies. Minus 3W. Because the 2 and the 2, they multiply and they cancel each other. Set this equal to 0. And solve. So, although this width is the only value that is given as our value for the 0 of the derivative, doesn't mean this is a maximum. I need to test this. So there are two different ways we can test, using the first derivative test or second derivative test. So I'll use my first derivative test here. Means I have to create a little mini interval chart. I know my width can't be less than 0, so I'm going to put 0 as my minimum, up to 200, and width above 200. Substituting A prime to get A. So if I choose a value between 0 and 200, let's say 100, put it into my first derivative, I get a positive value. If I choose a value bigger than 200, let's say 300, put in my derivative, I get a negative value, showing that I'm increasing and then decreasing for the original function. So therefore, W equal to 200 gives a maximum. Specifically a local maximum, but that's not necessary for us to find. So, what I need to do is I now need to find out the dimensions that will maximize this area. So I've already got my width. Now I can figure out my length. I can use this formula for L. Substitute 200 in, and I get a length of 300. And there I go. The length 300, the width 200 will maximize the area of the lot. Okay, and there we go. Problem solved. Let's try another problem. Okay. Cylindrical can contains 355 milliliters of liquid. The can is made from sheet metal where the top and the bottom cost twice as much as the sides. Determine the dimensions of the can that will minimize the cost of the can. Okay, well, cylinders, as we remember, one of the key parts of it is radius and height. Now, if you remember, there are two formulas that go along with this. There's volume of a can, that's pi r squared h, and surface area. Which is 2 pi r squared plus 2 pi r h. The 2 pi r h is the sides, and the 2 pi r squared is the top and the bottom. So, according to my information, I know my volume is 355 milliliters, which is 355 centimeters cubed. There's one equation. Second equation tells me that the price of the top and the bottom cost twice as much as the sides. Well, I don't know how much the sides cost, so I'm going to have to create an expression here. So what if we take the price as P, and we multiply it by our top and the bottom, and the sides. Well, since it's double, this is going to be 4p pi r squared plus 2p pi r h for our second equation. So I've created two variables here, so let C represent the cost of the can, and P be a constant, price for sheet metal. So constant means that it's always the same value. Although it's a variable, it's like a value like pi is. Okay, so I'm going to take my first expression. I'm going to solve for, probably h would be easier. So h would be 355 divided by pi r squared. Now I'm going to take this and I'm going to substitute into my second equation. Okay, so I get cost is equal to 4p pi r squared plus 2p pi r. Now I substitute h in. And now I get this expression. Okay, I'm going to simplify first before I even go any further. Oops. 2 times 355 is 710. P stays pi. Oop, that's a pi. Pi's cancel. One of the r's cancels with one of the r's, so this is r to the negative 1. This will help me find my derivative easier. Okay, so derivative of this to find the maximum is 8p pi r minus 710 p r to the negative 2. Set this equal to 0 and solve. Okay, I'm going to move this 710 p r to the negative 2 here. The p's are the same, so I can actually cancel that right off the bat. So I'm going to write this as 710 over r squared equals 8 pi r. Okay, I'm going to bring the r squared up and the pi r down. Just solve this. So 710 divided by 8 pi is equal to r cubed. So that means r is the cubed root of 710 over 8 pi, which is approximately, here's where I use my calculator, it's approximately 3.05 centimeters. Okay, so I need to determine whether this is a minimum or maximum. So, test for minimum. Well, this time, I don't want to use my interval chart. I would like to use second derivative test. So I've got to find my second derivative. So second derivative of this would be 8p pi plus 1420 p r to the negative 3, sorry. Well, no matter what value I substitute in, if r is positive, then c double prime will be positive. So c double prime, if r is 3.05, well, this is always going to be greater than 0. I don't even need to find out what it is, because if I substitute a positive value in here, all this is positive. So therefore, I know this is concave up, which gives a minimum. And there we go. We know we've got a minimum. So we need to find the dimensions of this, determine the dimensions. So I need to find my height. So I substitute back in to h, 355 pi. I substitute the 3.05 in there, and I get a height of approximately 12.18. Oops, forgot the 1. There we go. So we can, with a radius 3.05 centimeters and height 12.18 centimeters, minimizes the cost. And there we go. Problem solved. And thus concludes our lesson.